All right, here we are with week 15, chapter 12. This one's about solutions. So in this chapter, we're going to look at liquids and mostly with moles and liquids. So as we look at this chapter, we're going to think about the three parts of a solution. Solution was called a homogeneous mixture back in week 1. And now we're going to show you what that really means. So in this chapter, we're going to show you how to make a solution, what different types of solutions exist, how temperature and pressure affects the solubility of those solutions, and then eventually calculate moles from solutions, calculate percentages from solutions, and then use some stoichiometry for reactions using solutions. We'll also look at colligative properties of solutions, so how can they affect the boiling points and freezing points, and then we'll remind you about soap in the very end. So as we look at solutions, just remember that solution is the whole thing. So if we look at percentages later in a separate video, know that when we talk about the solution, we're talking about both pieces. So when you think of a solution, think of a homogeneous mixture that has two things inside. The bigger something we call the solvent. That typically is water. The smaller something, that's the little piece compared to the big piece, which was the solvent. The solute is the little piece, and that's usually like a sugar or a salt that we put into water. When we put things into water, we would call them aqueous. Aqueous is that AQ we've seen back in the solubility rules for spectator ions and the solubility table in general. So as we look at solutions, we just want to know that they dissolve, they disappear, they dissociate, and in this chapter in particular, we're just paying attention to the math behind that process. One of the first things we need to be comfortable with is recognizing a homogeneous mixture. Homogeneous mixtures are going to be things that look the same, top to bottom, left to right, front to back. Heterogeneous is where you can see that difference between substances that are mixed together. So as you look at these four choices, think of a hot cup of instant coffee. Instant coffee is kind of a brown powder when you put it into water. You stir it up and it kind of disappears because it dissolves into a solution. If you think about chicken vegetable soup, you can see the chicken, you can see the vegetables, you can see the soup. So those are all different. The problem with unfiltered blood is it likes to clot, and if it likes to clot, that means you can see a difference where it's clumpy here and not clumpy there. Very similar with a chrome-plated steel bumper. There's chrome on the front, nice shiny and silver looking, gives a nice little reflection just like a mirror. But behind it is probably a little bit of rust from that iron that's exposed to all that oxygen and that moisture. So as we look at these examples, just realize that this chapter is really only about this hot cup of instant coffee kind of example because you're putting something into the water. Water being the solvent, there's mostly water with one little scoop of instant coffee as our solute. There's many different types of solutions. There's liquids and solids. Liquids and solids are the ones that we're going to deal with most often. This would be things like sugar or salt dissolved into water. And water being the larger portion, and then we put in a smaller scoop of sugar or salt as the solute, and again, water being the solvent. Other things that are liquids and liquids are pretty common as well. We're going to see lab over this chapter using vinegar. We're going to be calculating the acetic acid mixed together in water, which it's about 5% that we're hoping to find in class. And then other drinks that contain alcohol would be in various amounts of water, like whiskey or beer or wine or so forth. All of those look the same. When you look at vinegar, it looks like water. It doesn't smell like water. When you look at alcohol, it may have a color, but it's going to be all that color, and that's because it's evenly mixed throughout. Some solutions you may not necessarily think about, and that would be solids mixed with solids. Because when most students think of a solution, they think it has to be in liquid form, and that's true even for solids. They were liquid at one point. So metal alloys are made by heating up metals, stirring them together, and making them uniform. So again, alloy solution. Both of those are great synonyms for homogeneous mixtures that we saw back in week 1 lecture. The common solid to solid mixtures that we've mentioned before was the 10 karat and the 14 karat gold versions. They're adding some copper and silver among other atoms to strengthen that gold. Also, we see here a picture of sterling silver. Sterling silver has small amounts of copper in the silver, and that gives it a little bit more durability. It gives it the resistance to want to tarnish to that dark kind of gray to black color that silverware tends to do over time. So again, solids and solids can still be solutions because at one point they were liquids, probably molten liquids, but then they were melted together and stirred up and looked the same in the end. As we look at solutions, we have a focus on water. Water is about 70% of our bodies by mass. It's about 75% of our brain, it's about 80% of our lungs, and it's about 70% of our surface of our planet. For this reason and more, water is considered a universal solvent. It's the key to life as we know it, and in most of those sci-fi movies, animals from outer space, or at least aliens from outer space, those are the ones that are coming here to try to steal our water in a lot of cases. The reason water is so important is because it's superpolar. It has a 1.4 electronegativity difference between OH covalent bonds. That's because oxygen's a 3.5, second highest on the table, and hydrogen's pretty low at 2.1. Because of its bent shape, it allows those dipoles to work together towards oxygen's lone pairs. Oxygen feels very electronegative, and it's going to attract other electropositive atoms through what we call hydrogen bonding. Side attraction, about 16 kilojoules we mentioned in the intermolecular forces chapter. The covalent bond itself, oxygen to hydrogen, sharing those electrons, is about 400 kilojoules. So remember, hydrogen bonding is the attraction between molecules, that's the glue. It's not the actual bond, even though it's called hydrogen bonding. So most of that was review, and it's good to review. It's good to see a lot of old chapters and now a new light. So as we think about solutions, think about 3 steps that are needed to make them. In order to make a solution from a ionic salt, you'd have to separate the solute. That means the sodium and positive and the chlorine negative ions have to separate. Remember, that's trillions upon trillions upon trillions of sodium positives and chloride negatives that have to separate. If this were sugar, it'd be the same kind of idea. You'd have trillions and trillions of sugar molecules that have to separate. So separating ions takes energy. If it takes energy, that's going to absorb energy from the surroundings and make it feel like it's getting colder. We saw this firsthand with some of our experiments early in the semester. If you remember back from the ice cube lab, either by video or in person, you probably saw or mentioned, or heard me mention at least, that baking soda in particular, sodium hydrogen carbonate, gets very cold when you stir it up into water. So cold that you have to warm it up with your hands to get it to the temperature of the salt water and the sugar water. So the ability to break ions apart or break hydrogen bonding between sugar molecules apart requires energy, and that forces the first step to get colder. The second step is solvent separation. This is the breaking apart of water. And because water is very polar, it's going to be attracted to other molecules, and it has to make room for those new molecules. So when we saw that layer of color sit on top of the sugar water in experiment 2, that was because of this solvent separation step requiring so much energy that most of the time it didn't break through. It formed a strong, dark-colored layer on top as a result. So because hydrogen bonding takes energy to break, in order to separate water molecules to make room for these new positive and negative ions, or potentially these new sugar molecules, either one, it's going to require energy and continue to get colder. So the first 2 steps require energy and make the solution colder. So the trade-off is, in the solvation step, do we get that energy back? If we do, then it's kind of a wash. There's just as much energy required as energy released, and it ends up being room temperature when you're done. The disadvantage for sodium hydrogen carbonate, when you stir it together, the first two steps require more energy than the third step releases, so therefore it stays cold, and then you have to warm it back up. It can also be the case, though, that the first two steps are pretty easy, and the last step is gaining new attractive forces between ions and water molecules. And if those new attractions were stronger than ones broken to begin with, that means we're going to now get warmer as a result. So keep in mind, all of this is happening simultaneously as you throw a scoop of salt into water, throw a sugar cube into water. So let's look at them a little bit independently first. So the solute separation would be the little guy, the little piece of our solution separating from itself. So in order to free these ions, we have to use energy from the solution itself, and that's going to get it colder. So you can imagine in this situation, water is going to have to use its polarity. So if you can imagine a water molecule, it feels very negative on oxygen. It feels very positive on hydrogens. So that negative is going to attract those sodium ions. And it's going to pluck them out, kind of like sticking with a harpoon and then pulling them away from the crystal structure. You can also imagine that the opposite side of the molecule of water feels very positive. Oxygen feels very negative. And these hydrogens can act like little tweezers and pinch onto those chloride ions that are negatively charged and pluck them out, just like plucking an eyebrow, so to speak. So this situation of breaking the attractions of the original crystal structure is what requires energy, and that requires it to pull energy from its surroundings, and that's going to make it feel colder as a result. In the solvent separation step, what we have now is water has to make room from other water molecules. So as we have some hydrogen bonding between water molecules, we have very negative oxygens attracting hydrogens from other water molecules that are very positive. So that hydrogen bonding that is holding the water together as a solvent, this attraction has to be broken. Because those new chloride ions and sodium ions are now present in that forming solution, and the water has to move out of the way, basically, to make room for these new ions. So water has to no longer bond with itself, but now starts forming attractions with those new ions. And because water has to break apart from itself, it's going to again feel colder in this now second step of forming a solution. Our last step is solvation. Very different from salvation. Solvation here is the ability to make new attractions between water and the new solute, which in this case being pictured as salt. You can imagine something very similar though with sugar. Sugar would have a bunch of alcohols that it would have a very polar attraction to those waters through hydrogen bonding as well. With salt here, we have something unique, and this is ions forming with dipoles. So the ability to have these negative ions, positive ions, so if you have a negative charge, you're going to attract a partial positive hydrogen of the water. If you have a positive charge, you're going to have a partial attraction to the electronegative oxygen atom. These ion dipole forces are exactly what we used with acetone, acid, and water back in our paper chromatography lab. We have ions and we have superdipoles attracting each other. And if the energy of this attraction is stronger than the attractions that we broke from the solute to solute and solvent to solvent, then we warm back up. And if this change is, this new forming attraction is stronger than the original, then we get quite a bit warmer as a result. Another way to think about this process of solvation is to think of hydration. We have a hydrate lab that we just finished recently with the mold chapter. Eventually, we have numerous attractions to ions with water. And this is where we can really gain our warmth back, because we may have broken a few attractions between water. We may have broken a few attractions between sodium and chloride ions in the solute, but now we're gaining a tremendous amount of attractions to new water molecules. So we get that on the top, the bottom, the left, the right, the front, the back, and that's a decent amount of energy that we're gaining back. And if that's more energy than the first two steps, we get warm. If it's less energy than the first two steps, we get cold. And if it's about the same, there's going to be no change, and we're relatively room temperature before and after. So again, this is all about dissolving. Very different than what we see in, say, The Wizard of Oz, where they say that the Wicked Witch is melting when water is thrown on her. That's not very scientifically accurate, because if water were thrown on something polar like a witch, it would dissolve, not melt. Melt takes a lot of heat, and melting is a physical state. That means the witch could come back. Dissolving here would be breaking it apart, molecule by molecule, ion by ion, separating it into that solution. But again, this last step is the ability for the solute to separate, the solvent to separate, and then the solution to form in that solvation step. A great example of the result of these kinds of processes is hot packs and cold packs. If the first two steps takes a little bit of energy, but the third step, the final step, requires, in this case, produces a tremendous amount of energy, that's exactly what happens in most hot packs. When you snap that little tablet inside and shake it up, those first two steps might get a little bit cold at first, but the third and final step gets super hot, and then it stays pretty hot. Hot enough to, treat a patient. The opposite's also true with the cold pack. When you break that tablet inside and shake it up, it gets cold. And because the third step doesn't get enough energy back, it stays very cold in the end. So two great ways to understand solutions with things you might find in a first aid kit. One of the things that you can help understand how much energy of hydration there is looking at charge. So as we look at a couple examples here real quick, we can see that magnesium, group 2, has a +2. Sodium has a +1, it's in group 1. So if sodium's a +1, magnesium is a +2. The only thing better than that would be an aluminum +3, maybe a lead +4. Basically, you can think of more charge, more energy. So energy is going to increase with more charge because you would have more attraction to have to break. You're going to have more attraction to a higher positive charge than to a lower positive charge. So the easiest way to think about that one is higher charge, higher hydration energy. So magnesium definitely a winner here because it has a +2. You might also think the reason it's a winner is because it has more overall ions to hydrate. If you have a higher charge, magnesium has 3 total ions. It has a magnesium +2 and 2 chloride negatives, where sodium only has a +1 and a -1. You can imagine aluminum chloride would then have 4 ions, and lead chloride, if this is lead 4 chloride, it would have 5 ions. 5 ions means 5 times the amount of hydration. So as long as you can make ions, higher charge means typically more ions and more attraction to those ions. In a separate video, we'll come back and we'll talk about entropy. Entropy is a great way to understand why solutions are created in the first place. So we'll catch you in a separate video for that.